Sean Kelly's 2008 account of integral time reveals a recurring pattern in temporal description that harmonizes the theories of Whitehead, Sri Aurobindo, and especially Leibniz. This pattern divides time into three interconnected domains: the timeless domain of eternity, the domain of flowing time, and their integration into a complex, integral understanding and experience of time. For Kelly, the essence of integral time lies in understanding how these dualities interact, rather than prioritizing one over the other. This interaction has been called deep transcendence, an idea that can be effectively modeled using fractals. Moran defines an iterative process as one that produces the effects, products necessary for its renewal. This process is a tortuous process in which the final effect or product becomes the first element or first cause. Understanding this iterative relationship is crucial to grasping the dialectical nature of the interaction between stasis and flux, or between eternity and time. Fractals, with their inherently recursive nature, provide a convenient mathematical framework for describing this relationship. The recursive process inherent in fractal geometry reflects the cyclical interplay between the timeless and the temporal, making fractals an ideal metaphor for integral time. To further explain, consider the fractal structure, where each repetition builds upon the previous one, creating a complex and infinitely detailed pattern. This reflects the recursive nature of integral time, where the temporal flow and the timeless infinity continually influence and reproduce each other. In this framework, time is not a linear progression, but a dynamic, iterative process in which the eternal and the temporal coexist and create each other. By using fractals as a descriptive tool, we gain a deeper understanding of integral time. The iterative process in fractals provides a foundation upon which temporal experiences of the timeless realm are constructed and reproduced. This iterative interaction exemplifies the profound transcendence that Kelly describes, where the dialogue between dualities reveals a deeper understanding of time. David Bohm, Laurent Nottale, Roger Penrose, and Stuart Hameroff present theories that explore the emergence of time from a timeless quantum realm. Bohm's interpretation of quantum mechanics, expressed in terms of the transition between the implicit and explicit order, provides a profound framework for understanding this emergence. The implicit order represents a fundamental reality in which everything is interconnected, while the explicit order is the emergent, manifest world we experience. This duality suggests a deeper layer of reality from which the temporal existence we perceive emerges. Laurent Nottale's theory of scale relativity adds another dimension to this discussion by introducing the concept of quantum fractal spacetime. His theory assumes that the fabric of spacetime is fractal on quantum scales and transitions into a non-fractal classical realm as we move away. This suggests a scale-dependent nature of physical laws, where time emerges as a macroscopic phenomenon from a fractal, timeless microcosm. Penrose and Hameroff extend these ideas to the realm of consciousness. They argue that quantum processes in the brain are fundamental to the emergence of consciousness and connect it to the cosmological structure of the universe. This interdisciplinary approach suggests that the emergence of time, like consciousness, may be a fundamental aspect of the universe and may be intricately linked to quantum phenomena. W.H. Newton Smith's The Structure of Time, 1980, demonstrates the need to integrate scientific theories in the philosophical study of time. He argues that any serious philosophical study of time must engage with quantum mechanics, special relativity, and general relativity. However, Newton Smith's work primarily addresses special relativity, leaving a comprehensive treatment of general relativity and quantum mechanics open as a path for future research. Quantum mechanics, on the other hand, challenges classical concepts of time and causality by revealing probabilistic and non-local aspects of reality at the microscopic level. By integrating these theories, we can explore how time can emerge from the interaction of quantum processes and the curvature of space-time. Since Newton Smith's pioneering work, several scientists have undertaken the complex study of time, exploring its subjective and objective dimensions. It is possible to engage in a dialogue with these alternative theories, especially by drawing on the rich discussions on the nature of time, geometry, physics, and perception. Bucharest, Saniga, and Stuckey, 2003. In Mathematical Approaches to the Concept of Time, fundamental mathematical structures such as Clifford spaces, Cremona transformations, temporal operators, and relational statistics are important. These structures attempt to bridge the gap between human perception and physical explanations by attempting to relate mathematical models to the subjective experience of time. Method Saniga emphasizes the need to integrate aspects of human psychological experiences of time into physical explanations. A particular focus of his work is the variability of temporal experiences, moments when time speeds up, slows down, or even stops. Such changes are not only part of everyday life, but are also deeply evident in psychopathologies and states of consciousness. Saniga's innovative framework explores the inherent topological differences between spatial and temporal dimensions. He argues that while the linearity of spatial dimensions encompasses points, the linearity of the temporal dimension encompasses conics. This distinction is crucial to understanding how the temporal dimension interacts with the spatial dimension and why our universe exhibits a 3+1 dimensional structure. Using Cremona transformations, Saniga interprets this dimensional interaction between models and subjective temporal experiences and their physical counterparts. In this context, fractals, with their self-similar and recursive properties, reflect the nuanced and often non-linear nature of our perception of time. They provide a versatile framework that can encompass a wide range of temporal phenomena, from the seemingly smooth flow of everyday time to the sudden, disjointed experiences characteristic of certain psychological states. Furthermore, fractals and Cremona transformations are not necessarily contradictory. On the contrary, they can complement each other in providing a more holistic understanding of time. While the self-similar structure of fractals can intuitively represent the scaling and recursive nature of time, Cremona transformations provide a robust mathematical method for modeling the interface between spatial and temporal dimensions. The exploration of time through fractal models has been a growing field of research, particularly influenced by the work of French astrophysicist Laurent Nottale and others who developed fractal spacetime and scale relativity theories. Nottale's pioneering work, 1993, delves into the measurable aspects of fractal spacetime, but avoids making a connection to subjective temporal experiences. In contrast, Susie Vrobel, 1998, uses a fractal model to explain the subjective experience of time, drawing on Penrose's concept of insight and McTaggart's sequence. She interprets the variables in fractal mathematics in terms of how we subjectively perceive time and offers a framework that bridges the gap between mathematical abstraction and lived experience. First, fractals exhibit repetitive and self-similar patterns, similar to the intertwined cyclicity of time, seconds in minutes, hours, days, months, seasons, and years. This reflection of intertwined cycles can also be observed in the generational patterns of biological life, from insects to trees, and reflects birth, development, and death in a self-similar way. Second, fractals demonstrate the phenomenon of infinite surface area within finite space, similar to experiencing timelessness within the boundaries of time. This can manifest as perceiving a finite moment within the infinite continuum of time, describing the paradoxical nature of time perception. Third, fractals often describe naturally irregular landscapes, such as coastlines and mountains, suggesting the potential to describe timescapes. In this context, one can imagine a timeline enhanced by the topographic depth of a map, with time flowing slower uphill and faster downhill, providing a metaphor for the changing subjective speeds of time. Fourth, the fractal dimension provides a scale of complexity that represents an internal rather than an external dimension of time. This provides a mechanism for modeling the deepening of temporal experience, such as the acceleration of time passage with age, and reflects the increasing complexity of subjective time. Finally, mathematician George Jaroszkiewicz has explored the role of complex numbers in fractal patterns, further enriching the mathematical landscape of time perception. Nottale's framework focuses on extending the principles of relativity to include scale covariance, yielding a law that remains invariant under spatial extension. This expands our understanding from the realms of position and motion to scales of size and argues that the laws of the universe hold when viewed from a cosmic or microscopic perspective. Integrating this with the concept of fractal spacetime allows for a deeper exploration of temporal scales. To achieve this, Nottale uses a fractal spacetime model based on Feynman's insights into the fractal structure and temporal reversibility of quantum orbits. Nottale's model provides results consistent with existing physical models and reveals new insights by explaining how non-fractal classical temporality emerges from the fractally reversible dimensions of space-time. While Nottale, along with independent researchers such as Nassim Haramein and M.S. El Nashieh, have developed robust theories for fractal and Cantorian spacetimes, they have not fully explored the implications for subjective time. Susie Vrobel's work provides a solid foundation by paralleling fractal theory with subjective time. In developing and expanding these ideas, it is necessary to find a balance between mathematical rigor and the phenomenology of time. In the following parts of our series, a comprehensive model will be presented that takes into account both objective structures and subjective perceptions of time using the properties of fractals. Thanks for listening, and take care.